Hi, this is Oleg Pinos. Today I want to talk about a concept that really matters in exploration: minimum economic field size, or MEFS. Put simply, it's the smallest field size that still pays off financially. Whenever we are involved in exploration or regional assessment campaign, one big question always comes up. How do we know if a discovery is big enough to be worth developing? In fact, that's a key issue, since history is full of examples like this. A company rushes into a project, they drill, they celebrate a discovery, but then reality hits. What looks great in the subsurface simply fails to deliver returns. And that's exactly where MEFS should come in. Its mission is to keep our attention on the economics right from the start and save us from costly missteps later. Now let's explore how this concept works in practice. We'll look at the key factors that shape MEFS and then bring it to life with a real-world example. I think you'll be surprised to see what really drives economic size.
Let's start with a formal definition. Here is the structure. It looks big and attractive on the map, but structure alone doesn't pay the bills. The key question: how much volume lies above the economic cutoff? By shifting the fluid contact step by step, we find exactly where the prospect becomes economic. Now watch the key value, NPV. Contact depth is 2640, 30, 20. At this level, we've entered the zone of negative NPV, where losses begin. Now, if we shift the contact just a few meters down, NPV rises to nearly zero, and right here is the minimum economic size. Plotted precisely, it comes out at 15.2 million barrels, the point where NPV hits zero, the cutoff between positive and negative economics. Bottom line: MEFS, or minimum economic field size, is the smallest discovery that is still profitable to develop. The next important point is that MEFS is assumption-driven, and that brings us to how different inputs can shift its value. Think of project economics like a set of scales: cash inflows on one side, cash outflows on the other. The project is either positive or negative, depending on which side is heavier. MEFS is a point where the scales are nearly balanced. But here is the key: the parameters on the scales are never constant. They are variables. Their values shift as economic assumptions or technical conditions change. Consequently, MEFS is a dynamic parameter. It depends on the assumptions we make and can change as economic or technical conditions evolve. Thus, we have two groups of variables that affect MEFS. First, economic influencers. Things like oil and gas prices, capex, opex, taxes, discount rate, and fiscal terms. Second, technical or geological factors: reservoir size, thickness, permeability, recovery factor, production profiles, and so on. Even though MEFS is affected by many factors, only a few are used to define its numerical value. In common practice, MEFS is most often expressed as a volume of recoverable hydrocarbons, which is the simplest and most widely used approach. Sometimes it's expressed as the area of the accumulation, but that requires assumptions about formation thickness and recovery factor. Another approach is break-even prices, commonly used for shale oil or gas projects. This map shows the price thresholds for 3 US onshore regions. Finally, some companies present MEFS as a statistical range rather than a single number, which helps to visualize the uncertainty in the estimates, a probability distribution, or a scatter plot. Why is this concept important? Take this play in a real basin as an example. Originally, there were 40 prospects. We calculated MEFS and used it to filter them. As a result, only 15 remained, the ones with real potential. This highlights the importance of MEFS, as it helps exploration teams focus on the right things. In other words, it frames our efforts in economic terms from the very beginning. Without it, we risk spending years of effort and millions of dollars on projects that will never make money. As we defined earlier, MEFS estimation involves finding the relationship between resource size and NPV and identifying the points where NPV equals zero. It is an iterative process that requires input from a multidisciplinary team to determine how resources, production, and economics interact. This can take a lot of time, especially when many variables are involved. Using traditional 3D models, the process might take anywhere from 1 to 6 months. But there is a faster way, no longer months but just days. With our software tool Geonomix, you can create value chains across the entire calculation process. It lets you estimate MEFS almost instantly and see how it changes when other parameters or factors shift. Now let me quickly remind you what Geonomix is. It's a software tool for integrated assessment of oil and gas projects. The key difference is that the entire workflow from geology to economics runs on a single unified platform. That means you can test scenarios and uncertainties almost in real time. And of course, MEFS, with all its possible variations, can be calculated practically instantly. Now let's dive into a real case and determine the MEFS. We are in an onshore basin where the Jurassic Plate has recently become a hot spot for exploration. Several prospects have been identified, and we'll focus on one typical structure for analysis. Let's open this in the program. We start the estimation process in the Geology module. The top surface is loaded and presented as a depth versus gross rock volume plot. First, we set the possible variation for the oil-water contact. This range reflects the typical structure field we see for this play. For the other parameters, such as net-to-gross ratio, porosity, saturation, etc., we define probabilistic ranges using regional data from our geostatistical libraries. We've covered this process in detail in our earlier videos. Once the volumes are calculated, we validate the results. For recoverable oil, the range between P90 and P10 comes out roughly from 2.7 to 25 per 7 million barrels. The tornado chart helps us see how much each parameter impacts the recoverable volume. Now we move into production module and turn resource volumes into production forecasts. First, we build a type well model using production history data from analog wells. Let's see, 51, 67, and the others. Next, we adjust the key parameters like the start rate and decline to match the actual well data. Finally, we add a probabilistic envelope to capture production uncertainty. This shows how a typical well is likely to perform over its lifetime. Next up, we scale type wells to the full field. Using recoverable volumes and the defined well type, we calculate the number of wells needed. Considering drilling rates and capacity constraints, we run a probabilistic field development model. And this gives us a probabilistic production forecast, which we then send to the economics. The economics start on the income side. We set the oil price with symmetrical variations over the first 20 years. Next is the spending side, CAPEX. This covers drilling and everything needed on the surface, like equipment, roads, and pipelines. All operating costs, such as lift costs and others, are fully included. Taxes are handled with a country-specific model through a dedicated calculator. Finally, the results are shown in the top panels and on the cash flow plots. Key indicators NPV, RIR, and others are calculated instantly, and cash flow reflects probabilistic outcomes. As shown in this diagram, the project appears mostly profitable except in the P90 zone. We call this diagram the value thermometer, where the NPV range reflects uncertainty in the initial field inputs. Now this is where MEFS comes to life, the program's unique analytics functions. This feature builds direct value chains across the entire process, from geology all the way to economics. That means we can pick any parameter, geological, engineering, or economic, adjust it, and immediately see how it affects the final economic results like NPV and others. Okay, let's see what really drives MEFS. First, oil-water contact, because it's the most uncertain input. Now watch as we shift the contact upward, meter by meter. Pay volume shrinks, and the NPV drops. Right here, where NPV is nearly zero, that's where MEFS sits. Simple. MEFS is the point where a field stops being profitable. Now let's look at the influence of oil price. Originally it was set as $60 per barrel, and we raise it to 70, then 80 and NPV gradually increases. Now we check the new MEFS under this higher price, shifting the contact further upward. Meter by meter. And this is where a new MEFS sits, somewhere between 2614 and 2615. The influence of the other parameters on MEFS can be analyzed further. For now, let's look at the final findings on the graph. And now, the most interesting part. Let's see what MEFS really tells us, and how we can push it down even further. Here you can see the first case we tested in the program. Each point represents a different oil-water contact and its respective NPV. And when we express MEFS in terms of recoverable oil, it comes out to about 5.16 million barrels. Now, what if the oil price goes up? In the program we tested it at $70, $80 and $90 per barrel. We can see MEFS gradually going down, but with each step the effect slows. That's the impact of the progressive tax system at work. Still, the improvement is clear. MEFS shifts from 5.16 to 3.93 million barrels. Next question. What if we switch to a different preferential tax system? You can see this leads to a much larger shift in MEFS. It clearly highlights the critical role of fiscal terms when estimating the economic potential of basins and regions. And finally, we tested the potential impact of transition to new development technologies. For example, horizontal wells and hydraulic fracturing increase contact with the reservoir. Enhanced recovery methods can push more hydrocarbons out of the rock. Even smarter completions and artificial lift can improve performance. All of these raise recovery, increase production, and as a result, reduce MEFS. In our case, we modeled a full switch from vertical to horizontal wells. And bingo! This technological change caused the most significant shift in MEFS, even more than changes in oil price or the tax system. Okay, this is the original situation. A lot of structures to analyze. We apply the original MEFS and get this number of prospects remaining. Then we switch development technology, get new MEFS, and this opens several more opportunities. This leads us to an important conclusion. Right technological upgrades are the key driver, opening the door to new opportunities across whole regions or basins. And of course, our program Geonomix is the right tool to analyze technological options, assess their impact on economics and MEFS, and ultimately uncover the key to new opportunities. Stay tuned.